In this video, we're going to discuss the logical connective OR. So let's recall, a logical statement is a declarative sentence that is unambiguously true or false. So for example, 5 is an integer is a true statement. -5 is not a rational number is false. 2 less than or equal to 5 is true. 2 cubed equal to 5 is false. Pi to the e less than e to the pi, you might want to check for yourself, is true. 11 is even is a false statement, and square root of 2 is an element of the rational numbers is a false statement. What's important here is each of these statements is unambiguously true or false, and so we refer to them as logical statements. Now in logic, there are four main connectives. They're not, also called negation, and, also called conjunction, and or, also called disjunction. And there's also implication. In this lecture, we'll discuss OR. So let's let P and Q be logical statements. Then the statement P or Q is the logical statement that's true when P is true, or Q is true, or when both P and Q are true, but false otherwise. We denote P or Q with a wedge, with a kind of V between them, and read it P or Q. So the truth table for P or Q is as follows, and just reflects the definition above. If P and Q are both true, then P or Q is true. If P is true and Q is false, well, P or Q is still true. If P is false and Q is true, it doesn't matter, just one of them needs to be true. So P or Q is true in that case. P or Q is only false if both P and Q are false. Now it's important to recognize that this is different from how OR is often used in ordinary language. So we need to make a distinction between the meaning of the word OR in mathematics and different meanings of the word OR you might encounter in ordinary language. So in particular, there are two senses, at least two senses of OR in ordinary language: inclusive and exclusive. So for example, if a waiter asks you, would you like soup or salad with your entree? Well, he means, and you understand him to mean, that you can choose one or the other, but you can't choose both. So that would be using OR in an exclusive manner, or using exclusive OR. In contrast to exclusive OR, there's inclusive OR. It's another way it's used in ordinary language. So for example, if you were to say of somebody that her grades are so good that she's either very bright or studies hard, well, that statement is not intended to exclude the possibility that both are true. Okay? So in mathematics, though, we can't take ambiguity. We can't accept ambiguity in the language of mathematics or logic. So we have to make a choice. Is OR going to mean exclusive OR is OR going to mean inclusive OR? Okay? And the choice that we have made historically in logic and mathematics is to always mean inclusive OR when we say OR, unless we say otherwise. And exclusive OR is often used in computer science. It's a perfectly legitimate meaning for OR. It's just in mathematics and in classical logic, we always mean inclusive OR. That's important to remember when encountering statements with OR in mathematics or logic. So one place where this has an important impact is in a statement like trichotomy. We stated it as, if x and y are numbers, then exactly one of the following are true: x less than y, or x equals y, or y less than x. So we really wanted exclusive OR here, but that's not how OR is used in mathematics, so that phrase exactly one was important. We had to use that phrase because OR, as understood in mathematics and logic, is meant to be inclusive. So we had to say that it wasn't inclusive in this case. So let's look at some examples. The statement 5 is an integer, or 2 is less than or equal to 5. That's true because both of these component statements are true. The statement 5 is an integer is true, and the statement 2 is less than or equal to 5 is also true. On the other hand, if we look at -5 is not a rational number, or 2 cubed is equal to 8, well, in that case, this is still a true statement. We can ignore the fact that -5 is not a rational number as false, because we know 2 cubed is equal to 8 is true. And just one of the component statements in an OR statement. It has to be true for the entire OR statement to be true. Finally, let's notice that if P is a logical statement, then P or not P is always true. So if we look at the truth table, we see if P is true, not P is false, and P or not P is true in that case. If P is false, not P is true, and again, P or not P is true. A statement that is always true because of its logical form is a statement we call a tautology. And in the end, all tautologies come down to this form, P or not P, for some logical statement P. So that's it for this video. Thanks for listening.